So students, in our last attempt, we actually discussed the dynamics of system of mass particles. We just quickly recapitulate what we have discussed so far. We discussed the kinematics part of the system of mass particles, where our system actually refers to the collection of n number of discrete mass particles moving independently of each other, suppose in a random manner in space. So we considered xyz axis, which is supposed to be the inertial reference frame, fixed to the ground with origin at O, and we handled a collection of particles wherein we isolated a general ith particle, and we went on actually locating that ith mass particle in various ways. We considered it reference frame from the fixed point itself. This green vector actually represents that position vector of this point. Then we located the same point with respect to an arbitrary point called A, which may belong to this domain of our system, or it may be outside a point of the system. So it is a totally an arbitrary point. And with respect to that arbitrary point also, we tried to locate this ith particle by this position vector rho bar I. When we referred it with respect to this fixed point, we called it r bar I. And then we take the center of mass of this group, I mean to say that the group of this collection of n number of particles, and we try to locate that same ith particle by means of this position vector. So there are three ways by which we located an arbitrary mass particle here, assuming the mass at this point is mi. So every particle is actually having mass concentrated in it. So the ith particle is having this mass called mi. And then we calculated the different kinematical parameters, starting with their position vector, then calculating the velocity of that of the group, from there the velocity of the center of mass of the system. Then we evaluated the parameter called linear momentum, which we said that it can be absolute or relative depending upon what type of velocity we are using in the linear momentum equation. If we express the absolute velocity, take the absolute velocity of the ith particle, we will be having the absolute linear momentum. If we use the relative velocity of the ith particle with respect to some point, maybe especially the arbitrarily moving point, as well as with respect to the center of mass, so we can calculate the relative velocity, translational relative velocity with respect to that particular point, and we calculated the relative momentum using the relative velocity in this case. And then we established various relations. Then in the same line, we derived the concept of the angular momentum, and that angular momentum we deliberately calculated with respect to this arbitrary point A. And then we see that how we can calculate it with respect to the fixed point by changing the point A to the origin O, and subsequently changing the suitable, using the suitable position vector. And we can take the angular momentum, find the angular momentum of the group with respect to the center of mass. Again, this angular momentum can be absolute angular momentum if we use the absolute velocity to calculate the angular momentum, and we can of course use the relative angular momentum also. And we established certain relationship and certain conditions under which we see that this absolute angular momentum and the relative angular momentum calculated with respect to any arbitrary point, when they will be equal, we evaluated certain conditions from there. And after that, we considered the kinetic energy of the group and saw that the kinetic energy of any group can be actually compartmentalized into two parts. One is termed as the translational kinetic energy. It is the kinetic energy of the system, and it can be compartmentalized into these two terms, where we have in the first group we have the translational kinetic energy, assuming the entire mass of the system to be focused with the center of mass of the group and moving with the velocity of the center of mass and the corresponding kinetic energy that we will be having. This one we call this as to be the translational kinetic energy. And then we have the remaining part of the kinetic energy, which will be possessed by the group because of the fact that all individual particle is having some relative motion with respect to the center of mass of the group, and thereby we have the relative kinetic energy term in this equation. So and then finally we observe that this is these are the basic important kinematic parameters that we require to discuss our kinetics portion. And we observe that the rigid body, because we said time and again that this particular chapter basically serves the building block of our part 2 study of dynamics, which is called the dynamics of rigid body. And we identified at this point that the rigid body can be defined as collection of such infinitely many mass particles. Obviously, those mass particles, distribution of the masses within the domain of the rigid body will be, geometric domain of the rigid body will be continuous. So masses will be distributed in a continuous manner within that geometric domain, and subsequently we can think of that continuous distribution of mass within the geometric domain as to be the collection of infinitely many mass particles, such that if we take any 2 points on the geometric domain of the rigid body, we will find that the distance between the 2 particles is going to be always constant. So that is actually our, we will see the implication of this sentence a little later, and we will try to focus on the fact that what does that distance between any 2 particles is going to be constant really mean so far as the dynamics of the whole thing is concerned. So with this introduction, I just quickly recapitulate what we have discussed in our earlier section when we discussed this the dynamics of system of mass particles. Now we today we will be discussing the kinetics part of this group. So again, just recapitulating the thing, we say that this is the ith particle of the group. As we have already stated, that this is the mass mi, and we see that these are the 3 position vectors by which we can, of course, locate this ith particle in space. So either it can be done with respect to this fixed point, or it can be done with respect to any arbitrary point, and there can be another way of representation of the thing, that we can have the center of mass of this group. We can have here the center of mass, and from there the center of mass, from there also we can actually locate this ith particle by this position vector, which we call it as rho bar I. So this is the center of mass. We can say this group, this is the center of masses location at this instant, and this is how we can have the 3 ways of locating this ith particle. Now, if we particularly, since we are dealing with the kinetics, so first we will talk about the forces that are acting on this ith particle belonging to the entire group. So we can draw the free body diagram. This part of this section is basically called the free body diagram. In this free body diagram of the ith particle, let us suppose that the sum total of all the external forces which are acting on this ith particle, I can consider them find out their resultant, and I can express it by this red vector which I call F bar I. This F bar, capital F bar I, thus represents the resultant of all external forces acting on this ith particle. This is the ith particle, let us suppose, and we take only the account of the forces, external forces which are acting on this ith particle. Along with this force, we will be having other forces also. We may have or may not have, but there will be a possibility that we can have those forces. How we say these forces as internal forces. So what is actually meant by the internal forces? Remember, these are called external forces. That means the forces which are acting from the surrounding to the ith particle of the system. Now we have thus two things. This is, suppose this is the domain of the group. So we identify here this is the ith particle, and we have the system surrounding. So surrounding is having some interaction on this ith particle. So that interaction resultant of that on this ith particle, we call this as F bar I. And then we may have the other internal interactions. By that what we mean? Say there are other neighboring particles here belonging in the group like that, and this our ith particle can have interaction with all these neighboring or all the remaining particles in the group. So if we consider the sum of those interactions which are acting on the ith particle, we can call them, say, as F bar I. So this F bar I represents the sum of all the internal forces which are acting on this ith particle. So if we suppose in that way we have, therefore, you see here we have therefore two kinds of forces. One will be this resultant of these external forces, and another will be the resultant of all such internal interactions, and we use them by these two vectors. And obviously we see that the total resultant of these two, its effect will be the net acceleration of this ith particle, absolute acceleration of this ith particle, which I represent it as A bar I. Now before we actually go and focus on to this issue, let us consider the try to find out the we try to focus on, discuss it in a more meaningful manner on this the internal forces which are acting on this ith particle. Suppose we are considering a system. Here we are having totally n number of particles in the group. Let us suppose that we are specifically taking a system which consists of three mass particles. One is Mi, another is Mj, and another one is Mk. So these are your three mass particles. So for us, n is equal to 3. How these mutual interactions can take place? If we consider particularly, say, the mass particle Mi, then definitely we may have the interaction of this ith particle with the jth particle, as well as the ith particle with the kth particle. So if we particularly consider this mass particle Mi, then these two interactions, possible interactions, can be defined as, say, F bar Ij and F bar Ik. Note this I inner subscript I use to indicate that these are the forces acting on this ith particle, and the outer subscript indicates who are actually applying this force. So F bar Ij indicates the force, internal force, which is acting on the ith particle because of the interaction, its interaction with the jth particle. Exactly in that same manner, when I say F bar Ik, it refers to the fact that it actually represents the interaction that this ith particle is having with the kth particle, and as a result of that interaction, the force, the internal force that is acting on the ith particle, can be arbitrarily represented by this vector. and we can say this is f bar ik. We show here all these vectors as outgoing vectors. It is shown arbitrarily. They can be incoming also. That means the sense of this vector can be in the reverse direction. However, one thing is important. When I consider such interaction for the jth particle, I find that since these are the interactions between only these two particles, so it means that when I consider f bar ji and f bar jk, we need to remember this f bar ji will be basically equal and opposite to this f bar ij, and this kinds of, for remaining particles, this kinds of relationship will exist. Why it is so? It is because Newton's third law. It is because Newton's third law. That means it is the action reaction. So all these forces are basically the action reaction pair, because the interaction this ith particle is having with the jth particle, that same interaction will jth particle will see, but in the opposite sense to the previous one with the ith particle. So it is pretty clear that if I interchange the subscript, that means f bar ij, when I interchange the subscript to f bar ji, they too will have equal magnitude. These two vectors will be having equal magnitudes, but they will share the opposite sense, and that is being reflected by this negative sign. So this will be true for all the remaining other two particles as well. And this, is a thing that we show it for, say, typically for 3 particles. If we go for 2 particles, or if we go for 10 particles, or if we go for 1005 number of particles, these interactions will hold good. So by method of induction, we can say for all n, whatever be the value of n, such relationship between the particles, the interactions relationships between the interactions with respect to the remaining particles, they will be going to be true. So having this in our mind, let us now focus on this ith particle. And we already have explained that this resultant of these two forces will ultimately give us the acceleration of this ith particle measured with respect to this absolute reference frame xyz. So if I refer a bar I, which is called the absolute acceleration of the ith particle as measured from this inertial reference frame, obviously what we can write is this: f bar I plus small f bar I is equal to mi a bar I, and it is pretty obvious that f bar I is representing the sum of all the internal forces. So I can say that it will be f bar I will be equal to summation j from 1 to n f bar ij, because it represents, suppose if I consider this ith, say with this n equal to 3, so what will be the total resultant of all the internal forces acting on the ith particle? Obviously it will be f bar ij plus f bar ik, because these are only the two particles with which it is having interaction. So therefore we can write in a general manner, we can say that it will be summed from j equal to 1 to n f bar ij. Only thing here, this subscript j and I, they will not be equal. Rather, we write it in this manner that j will not be equal to I. So the summation here that we are using, this sum will not be equal to I. It means that we do not have the interaction of the ith particle with the ith particle itself. That means there is no such term called f bar ii. This term, it does not exist. So since this term does not exist, so we need to remember that here our running variable j, the sum is this. This is the sum on this variable j. We are calculating the sum on this j number of jth index, and this jth index should not be equal to obviously the I. And It is because that we don't have any interaction called F bar II. That means the interaction of the ith particle with the ith particle itself. So that kind of interaction obviously physically does not exist. So we have, this is the Newton's second law. From Newton's, we should say Newton's second law. Newton's second law, we can write that this is our, the equation. It is true for every ith particle. So we can write that this is true for all I 1 less or equal to I less or equal to n. That means this is not only true for the ith particle, it is true for any particle in the group. So summing, this is written for a single particle. So if I now write the same type of sum for all other particles and then totally sum them up for the entire group, what we can write from here? We can say that summation F bar I varying from 1 to n, it is because we have n number of particles, plus summation I varying from 1 to n small f bar I is equal to summation I from 1 to n mi ai bar. So this is the thing. That means we are now, this is, we repeat, this is written for the ith particle. This equation is written for the ith particle, and we are now summing, because we are having n number of particles in our system. So we need to write for all n number of particles such type of equations, and then we write, say suppose if we have 2 particles, then we have to write for 2 particles, we will be writing our equations as f bar 1 plus small f bar 1 is equal to m1 a1 bar, and then we will be having the next equation for the second particle f bar 2 plus small f bar 2 equal to m2 a bar 2. So if we have in that manner, say 3 particles, so we will be writing now the third equation. So going in that way, if we have n number of particles, we will be having n such equations. And when we are having these n such equations, what we are doing, we are adding those n number of equations with respect to each other. So if we add them, so obviously this will be the summation. So it will be the sum in this manner. And if you remember what is f bar I, we say that f bar I is being given by this particular thing. So ultimately we can say summation f bar I can write them as f bar e. What does this f bar e represent? Now it represents the sum of, this we can say it is the resultant of all external forces. So we can say it is the resultant of all external forces acting, resultant of all external forces acting on the system, So the system means your n number of particles, correct? So this is the acting on the system. So we find that it is written here that f bar e represents the resultant of all external forces acting on the entire group. So that is our resultant f bar e. And we can see that this f bar e, we can write that this is the thing we can say, and we write that this equation, we see that we will be writing this, and we just note from here that what happens to this sum, this we identify as to be the resultant of all the external forces. But what will happen to this sum? In order to understand this, we look at this example once again that we created for n equal to 3 number of particles. So see here, when I am actually doing this double summation, actually you see this is the double summation. Double summation means I am doing it for the entire group. So if you refer to this example, when I am doing this double summation in this group, I mean I add this plus this plus this plus this plus this plus this. And since you know that here, because of Newton's third law, this kind of relationship exists. So we can therefore find that if we sum them all for n equal to 3, this double summation will simply vanish. So we see that this will become a null vector. As a result, we see that this double summation ideally vanishes and we are left with only this f bar e, and that is equal to mi ai bar, right? So we see that sum of all the internal forces that is acting in a group, that is going to vanish and it will not exist because of the fact they are all action reaction pair, Newton's action reaction pair, and ultimately we can write this ai bar, that is the absolute acceleration of the ith particle, by this equation, because we are using the absolute acceleration, so we need to use the absolute position vector. And remember, the absolute position vector of the ith particle is what? Which is being measured with respect to the point O, which you know is a fixed point. So this is absolutely fixed point. So the position vector of this ith particle, as represented by the vector r bar I, will represent its absolute position vector, and its single derivative with respect to time will give the absolute velocity of the ith particle, and the double differentiation of this position vector with respect to time will give us the absolute acceleration of the ith particle as measured from that inertial reference frame. So ultimately we see that this, we can write it in this manner, and we can say that it is being given by summation I from 1 to n mi second derivative of this absolute position vector. We write, since your mi is going to be constant, so I can take this mi inside the differentiation and summation, and we can interchange this summation sign and the differentiation, because we know that sum of the derivatives is equal to derivative of the sum. So if we remember that, then we can see that we can interchange this derivative and the summation sign, and can bring this derivative outside of the sum and can pass the sum inside, and ultimately we can therefore say that f bar e will become equal to the second derivative of this sum, which is and in place of this we can write that from our kinematics discussion, we know that this is basically equal to mc's into r bar bar, where r bar bar represents the position vector of the center of mass with respect to the fixed point. That means if this c indicates our center of mass, then its position vector with respect to this absolute fixed point, this will represent this vector. That means O to C. If we join this line O to C, I am not joining it without, because the drawing will get cluttered. So you see here, if I joined this position vector of this center of mass with respect to the point, that means if we use the vector OC bar, then that would represent the absolute position vector of the center of mass of the group, and we can say that absolute position vector, we can write it as r bar bar, and we can say this in this manner. So it will represent basically mc's into r bar bar, and we need to take the double derivative of this, keeping in mind that this position vector is basically function of time. So if we pass on to this derivative, and we can write that in this manner, because your mc's is going to be constant, it is not changing with respect to time. So we can say therefore, that means we are dealing with a constant or steady mass, where the mass is not changing with respect to time. Total mass of the system is not going to change with respect to time, but there can be the variable mass dynamics, where this rule will not be applied, and separate algebra of or law needs to be formulated for such cases. However, our case is not of variable mass dynamics, so our case represents that this system's mass is not going to change as with respect to time. So I can therefore say that f bar e, which represents the sum of all the external forces acting on the group, as disclosed by the free body diagram, and I can write that this F bar E will be ultimately given by mc's into acceleration of the center of mass of the group. So this equation pretty much looks like our Newton's equation, second law, which is applicable for a single particle. So that's why when we are applying or extending our Newton's second law from a single particle to a group of particles, we need to remember that we need to use the acceleration of the center of mass of that group and can safely apply Newton's second law, and we need not actually bother about all the internal forces that will be acting on this group because of their mutual interactions do not survive till last. So we need to consider only the external forces which is acting on the group, and we find their sum and its resultant will be ultimately equal to mc's into a bar, and this particular equation is basically termed as generalized Newton's second law of motion, because we need to remember that Newton's second law of motion is applicable for a single particle, but we can use that single particle equation and we can use it for a group of particles, but we need certain modification that this will be basically equal to, we need to capture the center of mass of the group, and then we need to calculate the acceleration of the center of mass of the group, and then we can apply this equation safely to the, as if assuming that the entire mass of the system is actually being focused onto the center of mass. Instead of considering n number of particles, we are considering a single particle that is the center of mass of the group, and we are assuming that all external forces which are acting on the system is basically they are acting on the center of mass, and therefore we find their resultant or the total effect and equate it with this particular thing, which is referred to as Newton's generalized second law of motion. Now the above equation can also be written, particularly if we see that we can write this equation as, this we can say that it is d dt of summation I from 1 to n mi vi bar. Particularly one differentiation I can take it. That means here I could have written this equation in this manner as well. I could have said that this is d dt of summation I from 1 to n. We could have written this equation as mi vi bar, where vi bar is nothing but dr by I dt. So this actually represents this entire sum basically represents the total linear momentum, absolute linear momentum of the system, or we can write it as gc's. Since it is the time derivative of gc's, we therefore can write this equation in this manner. That means F bar E can be written as gc's dot. That means we can write it in this manner, that we can integrate this equation with respect to time. That means we first multiply this equation by the scalar dt and then integrate this equation, and obviously what we will be getting is the statement of the linear momentum impulse equivalence relation. So this is actually linear momentum impulse equivalence relation. This we can say this is equivalence relation. That means this side represents the linear moment. This represents the impulse, linear impulse of the external forces which is acting on the group between the two specified time limits, and that will be equal to the change in linear momentum of the system evaluated with respect to these two time points. That means this is basically equal to gc's. We can write this in this manner, that this is equal to gc's at time t2 minus, we can say this is gc's at time t1. So we can write it in this manner. So we see this is how we can write and can rediscover our previous linear momentum impulse relation that we have already studied for a single particle. Now once I do it, so this is actually being done for so far as the forces are concerned. Now let us consider the moment of these forces, and we are calculating this moment once again. If you recall that when we are trying to calculate the angular momentum, which also represents the moment of the linear momentum, and during that point of time basically we took the point A, the arbitrary point, as to be our moment center or the center of moment. So following the same line of action, we now take this arbitrary point A and try to calculate the moment of these external forces and internal forces which are acting on the particle with respect to this arbitrary point A. So accordingly, what we are going to do, we are going to write our equation in this manner, that it is the summation I from 1 to n rho bar I cross, this will be, we see that this represents the sum, that is if we write this as f bar I only. F bar I represents the sum of all the internal forces acting on the ith particle. So basically what we have done in this step, is just consider this equation, because they are actually, it is referred with respect to the ith particle. We take the moment with respect to point A. That means when we are taking it with respect to point A, we need to remember that we need to use this position vector rho bar I. So as a result of that, we can say from here that we take the moment and we can see this, we can write it for a single particle, and then we can use the sum in order to write for the entire group, and thus this represents the total moment of all the external forces as well as the internal forces with respect to point A. So we can say this is m bar A. M bar A represents what? This is the total sum of the momenta of all the forces, external forces as well as the internal forces with respect to point A. Now we can of course write this equation distributing the cross product in this manner. See here, we write this, before we go and say this statement of simplification, let us once again consider, say, two particles here. That means we are assuming, suppose our system consists of only two numbers of particles. So that is, we take this special case just to explain this particular sum. So again, if I have, suppose there are two particles mi and mj, so these will be our total system of internal forces, and we are having the point A, for which, with respect to which, the position vector of the ith particle is rho bar I, and for the jth particle is rho bar j. So when I am going to write summation I from 1 to n rho bar I cross f bar I, that means here actually since n is equal to 2, so obviously our sum will be for only two particles. So we can write it in this manner. That means it will be rho bar I cross f bar ij plus rho bar j cross f bar ji. Remembering the fact that f bar ij and f bar ji are equal and opposite, so we can ultimately write this equation. In this manner. We can say that summation I from 1 to 2 rho bar I cross f bar ij is basically equal to rho bar I cross f bar ij plus rho bar j cross f bar ji, and this f bar ji is basically equal to minus f bar ij. So ultimately what we have, that this equation can be written as rho bar I minus rho bar j, that means this vector minus this vector cross f bar ij. And you know that rho bar I minus rho bar j, this vector basically refers to what this vector will be there. You see, this is the vector we will be getting. So this is the vector that we will get, that is the vector here. So this pink vector basically represents our rho bar I relative to j. Sorry, we can write it in this manner. This is rho bar I relative to j. So this pink vector represents rho bar I relative to j. And we note that this rho bar I relative to j and this vector f bar ij, they are collinear. That means they are identical, sharing the same sense or the opposite sense. And naturally, their cross product, that means we know the cross product of two collinear vectors is always going to be null. So as a result, we find that this actually, this actually becomes equal to null. So going by the induction, this we verified for n equal to 2. But going by the induction, we can say that this sum, you see, this sum does not exist. So we can therefore say that we can write from here that summation I from 1 to n, rho bar I cross f bar I, that is going to be equal to null. Correct? So this is going to be equal to null. This is the sum. When we are representing the entire sum, this sum is actually vanishing. So ultimately, what we are left with is the moment. We are left with only the moment of these external forces with respect to the point A, because this is the term only it is now surviving. So we can therefore say from here that the sum of the momenta of all the internal forces about an arbitrary point is coming out to be as 0. As a result of that, we can see that the moment m bar A, that means the moment of all the forces with respect to the point A, is basically equal to summation I from 1 to n rho bar I cross f bar I. That means again, we do not have to take into account the moment of all the internal forces, and ultimately we can write our equation in this manner, that is m bar A is equal to summation I from 1 to n. We can write this equation that m bar A is basically equal to summation I from 1 to n rho bar I cross mi ai bar. That is what we are getting. This is the summation of m bar A, which is the the sum of the momenta of all the individual external forces acting on the group, and that moment is basically equal to this one. Now once I derive this equation, let us recall our relative angular momentum expression with respect to that arbitrary point, which we have already studied in our kinematics section. So recalling our equation for the relative angular momentum, which is calculated with respect to point A, if you recall that since it is relative, we need to use the relative velocity of the ith particle with respect to the point A. So accordingly, we see that this basically represents summation I from 1 to n rho bar I cross mi into vi bar minus va bar. So this represents the relative velocity of the ith particle with respect to the point A, about which I am calculating the angular momentum. So I need to take the moment of this relative momentum in order to calculate the relative angular momentum with respect to point A. Also, we note that rho bar I basically equal to, if we go back to our original figure which I have represented here, we need to consider from here that see the rho bar I. So this is representing rho bar I. What this rho bar I is actually equal to, this is clearly as seen from this triangle, this rho bar I is basically r bar I minus r bar A. So the relative position vector of the ith particle with respect to point A can thus be written as equal to r bar I minus r bar A. So remembering that, if we now take the derivative of this equation with respect to time, I will be writing h bar A relative dot. That means we are taking the derivative of this equation, and following the UV method of differentiation, we can say this will be equal to summation I from 1 to n. It will be the derivative of this position vector cross this term remaining unchanged, plus then this will remain unchanged cross mi derivative of this velocity term, which will ultimately give the acceleration terms. That means it will become rho bar I cross mi ai bar minus a bar a when the sum is taken for the entire group. Now if you particularly see what does this rho bar I dot represents, this rho bar I, as it is being given here, rho bar I dot obviously will represent the derivative of this with respect to time. That means it will be representing vi bar minus va bar. So ultimately the first term, group of terms, we see that ultimately the first group of terms is written like this. It is the summation from I equal to 1 to n. In place of this rho bar I dot, I can write it is vi bar minus va bar cross mi vi bar minus va bar, plus I can say, I can break this term, I can write this is plus summation I from 1 to n rho bar I cross m bar ai mi ai bar, sorry, minus it is summation I from 1 to n rho bar I cross mi a bar a. So see here, these two vectors are basically same, and obviously the cross product between them is going to be null. So therefore this entire term the sum of this entire terms is going to be equal to null. So as a result, we have a lot of simplification, and ultimately we see this equation boils down to summation I from 1 to n rho bar I cross f bar I plus this, because mi ai bar, we know that this this particular fact I could have written here plus small f bar I rho I, but we know that when we are taking this sum, we already have noted that this sum is going to be equal to null. So suppressing that term, ultimately what I can write that this directly I can say in place of mi ai bar, I can directly write it to be equal to fi. It is because here we can mention here it is because since we know that summation I from 1 to small n, we can say rho bar I cross f bar I, that means the sum of all the internal forces acting on the ith particle, and we are taking the grand sum, this sum is going to be null. So since this sum is going to be null, we have not written that here when I am writing it in place of mi ai bar, because mi ai bar is basically equal to fi bar plus small fi bar. But since that sum does not exist, so ultimately we can write it to be only equal to summation I from 1 to n rho I bar cross fi bar. We once again need to understand this. In place of mi ai bar, we can write that since we know that mi ai bar is basically equal to f bar I plus small f bar I. This is the fact. This is the fact, since this is the thing, and we can write from here that this sum, that means I from 1 to small n rho I bar cross small f bar I, this becomes equal to null. So ultimately we can see that in place of this mi ai bar, I can directly write only the moment of these forces, and we can write it in this manner. So ultimately what we see now, coming to the last term, we see that we have a negative sign, and we just considering the fact that this is going to be independent of the sum, So what I do, I reverse the order of the cross product and associate this scalar mi, instead of with a bar a, I associate it with the vector rho bar I. So making this minus plus and taking this acceleration a bar a outside of the sum, we get that this is equal to summation I from 1 to n mi rho I bar. And you know that when we are having this sum, instead of this we can write, since this is the center of mass, center of mass, so we can write it in this manner, that this being the representing the sum, we can replace it by this equation, which is the the definition of the location of the center of masses position vector with respect to point A, because we know that rho bar bar is defined as the position vector of the center of mass with respect to this arbitrary point A, and obviously rho bar bar will be equal to summation I from 1 to small n mi rho I bar divided by summation I from 1 to small n mi. That means I can write that rho bar bar is basically equal to summation I from 1 to small n mi rho bar I divided by mcs. So in place of this sum, I can write it in this manner. So ultimately what we find from here is this, that the derivative of this relative angular momentum is equal to the moment of all the external forces, sum of the moment of all the external forces with respect to the point A plus this term. So obviously, if we try to say under what condition or conditions these two terms will be equal, that means m bar A will be equal to the derivative of the relative angular momentum. Why this? We are considering this to be equal because just now when we discussed the force, we see that we have this type of relationship. When we considered the force, we see that we have this type of relationship. That means the sum of all the external forces acting on the system was basically equal to the time derivative of the system's linear momentum, right? Absolute linear momentum. So as a result of that, we note from here, in line with that query, we can of course investigate under what conditions these two will be equal. So specifically we have addressed this type of question also when we discussed the kinematics, particularly when we have come across the relationship between the absolute angular momentum and the relative angular momentum as calculated with respect to an arbitrary point, and we investigated the conditions due to which these two angular momenta will be equal. So going by that same logic, we can see therefore under what condition or conditions these two terms will be equal. Obviously when this term will be null, this entire group becomes null. So this will become null under these three conditions. First of all, we see that we may have this to be equal to null when a bar A becomes equal to null. Now the acceleration of A becomes equal to null. It means that the point A can have uniform velocity moving along a straight line. That means we can have a point A which is moving along a straight line. Does not actually is not to move about a curvilinear path. So the point A has to move along a straight line with a uniform velocity, and then for that case the acceleration of the point A will be equal to null. Or it is better that if you take a fixed point, because we do not have this condition that the point A will be always moving along a rectilinear path with a uniform velocity, so it is better that the acceleration of point A will be equal to null, obviously when the point A will be a fixed point. That means when A coincides with the point O. That means it means that if instead of taking any arbitrary point, had we taken the moment center as this fixed point, I would have said that the moment of all the external forces acting on the system about this fixed point would be equal to the time derivative of the relative angular momentum with respect to that fixed point. So under these conditions, you see these two will be basically equal. So that is the first possibility. The second possibility is that since your MCs cannot be equal to 0, so the second possibility is that when this vector is equal to totally null. So if we see that, if you see that what is rho bar bar? Rho bar bar represents the location of the center of mass of the group, of the entire group with respect to an arbitrary point A. So when I say this relative position vector, this is actually the relative position vector. That's why we denote it by the symbol rho. So when I say this relative position vector is null, so essentially that means that the point A and the point C are the identical points, because only under that condition this relative position vector is going to be null. So it means when the point A coincides with the center of mass of the system, that means instead of taking, once again I am going back to that thing, instead of taking any arbitrary point as our moment center, instead of that, had we taken the center of mass of the group as our moment center, and had we evaluated the moment of all the external forces acting on the group with respect to the center of mass, then I would have, this would be m bar c, and then I could write that m bar c is basically equal to the time derivative of the relative angular momentum with respect to the center of mass. And that's an interesting thing. We know when we studied the equality between the absolute angular momentum and the relative angular momentum with respect to any arbitrary point, we noted that if we would have taken, instead of A as an arbitrary point, instead of that, had we taken the center of mass as our reference point, I could arrive at the conclusion that the absolute angular momentum calculated with respect to the center of mass and the relative angular momentum calculated with respect to the center of mass are basically same. That means it will be the time derivative. So if we consider the center of mass as our moment center, then I can write this equation as m bar c is equal to h bar c dot relative. It is also equal to h bar c dot apps, because we know that h bar c apps and h bar c rel, they are basically equal. So it is therefore, you see that the center of mass serves a very unique purpose in our study of the entire dynamics for a group of particles, and going forward this will be also playing a very pivotal role in case of the motions of or dynamics of rigid bodies. So that is our second possibility. And of course the third possibility is that since we are dealing with the cross product between the two vectors, I mean to say the acceleration of the point A and the relative position vector of the center of mass with respect to point A, since we are dealing with the cross product of these two vectors, for the time being ignoring this presence of the scalar term in between them, we see that there is a possibility when these two vectors become collinear. That means when the acceleration of the center of acceleration of the point A, when it will be along this rho bar bar, or it is say opposite to rho bar bar. That means when A bar A and rho bar bar, when these two vectors become collinear, we see that with respect to that point also I can write this equation. Of course, this is a very special, I mean to say this third relation, situation is a very special type of characteristic, and we going forward when we will be discussing the dynamics of rigid bodies, we will come across to this instance when this arbitrary point A, selected point A, is selected in a judicious manner such that its acceleration, instantaneous acceleration, of course all these relations are instantaneous, its instantaneous acceleration is directed along or opposite to the relative position vector of the center of mass as evaluated with respect to this point A. So we see that this plays a very special, the type of thing when this condition is very typical one, and we will particularly try to highlight it when we will be studying the dynamics of rigid body in our upcoming discussions. So we can therefore say that either with respect to a fixed point or with respect to the center of mass of the system, we can say that m bar A is equal to h bar A, and we should add to this that it is also equal to, this is also equal to, because for both the fixed point as well as for the center of mass, they are basically also equal to h bar A derivative of this. Instead of taking the relative term, we can take the absolute term also, because we know from our previous discussion that both with respect to a fixed point or with respect to the center of mass, the relative angular momentum and absolute angular momentum are going to be equal. So we can add this condition also to it. So it is basically saying, or it does not matter whether I am going to write the relative momentum or angular momentum. So I can therefore just drop this over specification and can simply say this is equal to h bar A dot. So I can have this and I can write that, so I just drop this rel subscript from here, from both the terms, and we can write from here that integration from T1 to T2 ma bar dt, especially from this equation, last equation, h bar A as calculated at time T2. So we just write it in a decent manner. It is calculated with respect to the two time levels. We say that it is h bar A at time t equal to T2 minus h bar A at time t equal to T1. So if you take this, equate it, and I find that this will give us the equivalence relation. Again, this will give us the equivalence relation between the angular impulse and the angular momentum. Of course, this is going to be true when the point A is a fixed point, or when we take it to be equal to the center of mass of the entire group. And this particular equation represents what is termed as the principle of angular impulse angular momentum equivalence relation. So once we do with this, let us now come to the next kinetic parameter or kinetic issue, that is known as the work energy expression. So we see here, when we discussed for a single particle, we can see that we can write from here, that for a single particle, we can say that f bar I plus small f bar I is equal to mi ai bar, where you remember f bar I represents all the external forces which are acting on the ith particle, capital F bar I, and this represents the sum of all the internal forces acting on the ith particle. So considering the ith particle, applying Newton's second law, it is not actually generalized second law, this is actually from Newton's second law. We know from Newton's second law, we can write it from here. It is not the generalized second law. We know from Newton's second law of Newton, that f bar I plus small f bar I is basically equal to mi ai bar. So this is going to be true going forward. This is going to be true for all the particles belonging to our group. So if we assume that ds I bar, that means if this is our ith particle, suppose this is our ith particle, okay, and we have these forces acting on it. This is our f bar I, suppose the resultant of all the external forces acting on the ith particle, and suppose this is our f bar I, which is the sum of all the internal forces acting on the ith particle. So this is the thing, and under the action of these two, if let us suppose that this ds, under the action of this, we suppose that this is having a displacement, differentially small displacement, ds I bar. So what I do, therefore, I just take the dot product of this equation with respect to this differential displacement of the line of action of these two forces. That means this is representing the differential displacement of the ith particle having the mass mi. Okay, say that particle may be moving along a curvilinear path, and let us consider ds I bar, then that will represent a tangential direction along this curvilinear path of the motion of this ith particle. ds I bar represents the differential displacement of the ith particle, which will be of course tangential to the actual path followed by the particle with finite time. So if we take the dot product of this vector with this, obviously what we can write is that it is f bar I dot ds bar I plus small f bar I dot ds bar I is equal to mi ai bar dot ds bar I. Now you need to remember this ai bar represents the total acceleration of the ith particle, and when we are taking the dot product of this displacement, which is differentially small displacement, which is it is acting along the tangential direction, recalling our work energy equation, we know that this ultimately can be written in this manner, that it will be equal to, there we learned a bar dot ds bar is equal to v bar v dv. So actually it is, since it is there, it was a single particle, but since here we have a group of particles, we just add the subscript and nothing else. So basically we are dealing with that same work energy equation that we studied in our previous chapters when we discussed it for a single particle. So we see therefore this is equal to mi vi dvi. That means it can be written as dti, where one should remember that ti means what? Ti means equal to half mi vi square, which is the kinetic energy of the particle. So dti will obviously represent mi vi dvi. So in place of mi vi dvi, I can write that this fi dot dsi plus small fi bar dot dsi bar will represent equal to dti, and this is going to be true for all the particles belonging to the group. So as a result, if we try to sum this over the entire group of particles, I can write summation I from 1 to small n integration from s1 to s2 fi dot ds bar I plus it will be summation fi bar dot dsi bar, that will be basically equal to summation I from 1 to small n delta ti. That means this is delta summation I from 1 to n ti. That means it is equal to delta t system. And you remember T sys the last section of our kinematics discussion. TCs has two different components: translational kinetic energy plus the relative kinetic energy of the particles, individual particles, due to its relative velocity with respect to the center of mass. And difference of that, that means it is basically equal to, that means it is going to be equal to T6 2 minus T6 1, system's kinetic energy at these two configurations. The initial configuration, this 1 represents the initial configuration and 2 represents the final configuration. So we need to consider two separate spatial configurations. One we dub them as the initial one, and the other one we call it as the final configuration, and we try to calculate the kinetic energy of the entire system in these two configurations and take their difference, and that will be, the total work done here. This represents the total work function that we are having. Now we need to see in words. We can say that this equation represents the sum total of the work done. It is representing what? It represents the sum total of work done by all external and internal forces is going to be equal to the change in kinetic energy of the entire system. And this we can say as to be the principle of work energy equivalence relation defined for a group of particles. Now, so far, whenever we had this opportunity of the mixed kind of things, that means when we had the summation done for the entire group, when we have the presence of both the external forces and internal forces, we see for both force and moment calculation, the total force of the resultant of the internal forces for the entire group is equal to null, as also we see the total moment about any arbitrary point is also null. So let us try to see whether the work done by the total internal system forces for the entire system, whether it is going to be equal to null or not. That means whether this term survives or not. Now for this, you see, we need to therefore separately focus on the issue which is known as the work done by the internal forces. So again, for simplicity, we consider two particles. That means again we consider n is equal to 2 in our case. So what is going to be true for n equal to 2 is also going to be true for n equal to any number. So suppose we are having two particles, one having the mass m1, other having the mass m2, and these are your internal forces, F bar 1 2 and F bar 2 1 acting on them, and they are the displacement. So we can therefore say that for the entire group, we can say for the entire group, this summation F bar I dot ds bar I, here it happens to be the fact that when we are getting the sum F bar I from I equal to 1 to 2, this is equal to I equal to 1 to 2. That means we are actually calculating this entire sum. We know that this is going to be null, correct? And here it happens to be that F bar I, here it happens to be that F bar I, this actually represents only F bar 1. It is because we are having only two particles. Had we have say 3 particles, then there would have been the second term, correct? So here we see this thing. So therefore we know that if I just sum it out, I write that it will be, since it is done for the entire group, I need to take these two forces also. So I need to consider their individual work done. So the work done by this will be F bar 1 2 dot ds1 bar, because of the fact that the line of action of this F bar 1 2 is having this displacement ds1 bar. Exactly in a similar manner, the line of action of this vector F bar 2 1 is having this displacement ds bar 2. So therefore, this would represent my total work done. And remembering the fact that F bar 2 1 is going to be equal to minus F bar 1 2, ultimately you see we can write this equation as F bar 1 2 dot ds1 bar minus F bar 1 2 dot ds bar 2. That means I just replace this F bar 2 1 by minus F bar 1 2 and can write it in this manner. So for this entire group, I mean to say when our group consists of only two particles, I write that summation I from 1 to 2 F bar ij. That means actually I should have written it in this manner. I should have written it in this manner, that actually what we are going to write it here is like this. That means we are going to write summation I from 1 to n, right? This represents F bar I dot ds bar I is basically equal to, since our group consists of only two particles, I can say that this represents, you know, the summation F bar I dot ds bar I is basically equal to F bar 1 2 dot ds1 bar minus ds bar 2. And this, you know, is not going to be equal to null in general, unless obviously it can become null when these two are equal. That means this is the identical displacement both these particles are having. When they are the condition, this is the condition. Or it could be due to the fact that this and this are having a 90-degree angle between them, as also this one and this one is having 90-degree angle between them. So under these two special cases, so the first one is both the particles are having identical displacement. If that is the case, of course this total work done would vanish, because in that case ds1 bar and ds bar 2 will be equal. So that would be the situation when this total work done will be equal to 0. Or it will be the fact that if we individually consider that these internal forces are perpendicular to their respective displacement components, differential displacement components, again we note that this sum will be equal to 0. So from here we make a very important conclusion, that unlike the resultant of internal forces and their momenta about a point, which we have already seen, the work done by their resultant or the total work done by the internal forces is not equal to 0 in general. So this is going to be a very important observation that we are having. That means it is actually not that we can directly say that the sum of the internal forces, total work done by the sum of all the internal forces is going to be equal to 0. It is, of course, it can become equal to 0, but it is not a the necessity. So it can be equal to 0 under certain special conditions, but it may not be true for in general case. So that's the sharp difference with the, as far as the resultant of the total internal forces and the resultant of their total internal moments about any arbitrary point are concerned. They are equal to, we see that they do not exist. They ultimately vanish when we take the entire sum over the entire group. So we see that again, this is a very important conclusion, and with this we more or less touch upon all the essential features of the kinetics of the group of particles. Again, we need to remember here all the particles consisting of the group are actually moving with respect to each other in an independent manner. And again, we come and discuss the case of a rigid body, because we know that we have already mentioned time and again that ultimately this discussion, present discussion that we are doing with respect to a system of the arbitrary number of particles moving in an arbitrary fashion, will be ultimately leading us to the discussion of the dynamics of rigid body. So once again, if we consider a rigid body, mathematically rigid body can be defined as the collection of infinitely many mass particles. That means in the case when n tends to infinity, of course we need to have a continuous distribution of mass within the geometric domain. And if we take the distance between any two particles belonging to that domain, that is going to be constant. Thus, if we say, mathematically speaking, we can say if Mi and Mj are the two mass particles where Mi and Mj both belong to the domain set omega, which is defining the rigid body domain of the body, we see that for these two particles, the distance between these two vectors, that means the position vectors Ri bar minus R bar j, the difference between these two vectors, or that means we can say this is going to be equal to rho bar ij, rho bar I relative to j. So the magnitude of this rho bar I relative to j, the magnitude of this is going to be constant. Now this is going to be true for a rigid body. Also, it can be going to be true for a case when we have a rigid system. We can have a rigid system. So let us call this a rigid body, and this is going to be true for a rigid system as well. Now what is actually meant by the rigid system? By that what we mean to say is this: suppose I have a mass particle here and I have another mass particle here. Let us suppose that this mass particle is having the mass Mi and this is another mass particle having the mass Mj, and these two are interconnected by means of a light rod. So these two are interconnected by means of a light rod. So we can say this is the light rod. We can write this is the light rod. That means the mass of the rod itself is negligibly small compared to these two masses. This is a dumbbell model, so called a dumbbell model. It looks like a dumbbell, and this consists of, here we have taken two particles, we can have a third particle here also, fourth particle there, and we can go on building this type of system. So this is the most simple system when your rigid system consists of the total number of particles as n equal to 2, and you can have any number, and by that you can consider this type of system. And for them also this relationship is going to be true. And what does this relationship have any have the importance in our study of dynamics? First of all, we need to see that since the interdistance between the two particles is going to be always constant, the magnitude, so I can therefore say that the relative motion of one particle with respect to the other will be always a circular one. So what does that mean? It means that if this system is having some velocity, let us suppose that the velocity of this particle at a particular instant is vi bar, and let us also suppose that the velocity of this jth particle, the other particle, is v bar j, right? So what we can say from here, that since the relative distance between them is going to be constant, so I can write from here that v bar I, suppose it is equal to, we can write that it is equal to v bar j plus the relative velocity, we can say the omega angular velocity. We say that this will now, the body will now have some angular velocity. So it will be omega bar cross rho bar I relative to j. It is because of the fact that we are having, the distance between these two is going to be constant. How we are getting this equation? It is pretty obvious. We note that from here we can say we can take any we can take for that matter the absolutely fixed point. Let us say this is our absolutely fixed point O, and we measure these position vectors from this absolutely fixed point here. So suppose this is our position vector, this is another position vector defining the two particles. One is r bar I and another is r bar j. Remember, this relative distance between them is going to, that means this distance is going to be always constant. So I can write from here that r bar I, suppose we can write it this way, it is equal to r bar j plus we have, this is the relative position vector of I relative to j. That means this equation that we are getting. Now, if we differentiate this equation with respect to time, obviously what we get, it is having ddt of r bar I will be equal to ddt of r bar j, ddt of r bar j plus we have ddt of the rho bar relative I relative to j. So this is the thing that we are getting. Now it is pretty clear that this ddt of r bar I is going to be equal to v bar I plus it is equal to v bar j, and then we have this option. You see this option of finding out the derivative of a vector whose magnitude is going to be constant. So this is very important. Its direction may not be constant, but its magnitude is going to be constant. And that is only possible when we see that the direction may vary, but the magnitude is not. That is only possible when we are considering a circle, when we are considering an imaginary circle. Let us suppose, we can consider an imaginary circle here, and consider on this circle we have this ith particle, we have this mi, right? This is mi, and to the center of this circle let us have this mass mj. So we have this mass mi, and here we have this mass mg. So now here we note that the distance between these two, so you see this is the, and we can say that, say this particle mi can have a velocity which is this tangential velocity. Since this distance is always going to be constant, therefore the motion, relative motion, that means this time derivative is only possible when it is having this rotational motion. So it is having this angular velocity omega, and this will be its relative velocity. That means this pink vector ultimately represents rho bar dot I relative to j. That means this equation. So I can say from here, that this rho bar I, so we can say from here that this rho bar I relative to j, its derivative, is basically equal to omega bar of the system, so we can say it is omega bar system cross this position vector. That means this position vector, this green vector, you remember this green vector is basically your rho bar I relative to j. Okay, so we can therefore say that this is basically equal to rho bar I relative to j. So when we have the magnitude of the vector is not changing, magnitude of the vector is not changing, but its its direction can change. We know that this is the relationship we get. That means if we take the derivative of that, then that is going to be equal to this particular thing. It is because it is pretty obvious from the example of the circular motion. So going in that way, I can say that this is going to be plus, this is going to be plus rho bar I relative to j dot. That means I can say from here that V bar I is basically equal to V bar j plus we have this omega bar cis cross we get rho bar I relative to j. So that is the equation that we are getting. Now this is of course true for the velocity equation when we have our system consisting of a rigid system, and here we are taking the case of an example when we are having the number of particles associated is 2, and this is going to be true for any number of particles. Now we can write from here, say from here we can say, if we further, for example, if we take this equation further, and if we had gone for the differentiation of this equation one more time, that means we can have this rho bar I double dot, that will be equal to, you see, this will be omega bar cis dot cross rho bar I relative to j, right, plus we have omega bar cis cross rho bar I relative to j dot. So it is simple, just UV method of differentiation, we get this equation. So it means from here that rho bar I relative to j double dot, which represents the relative acceleration of I with respect to j in case of this motion, basically it is equal to omega bar cis dot cross, this represents angular acceleration of the system, cross rho bar I relative to j, plus we see this will be equal to omega bar cis, remembering the fact that rho bar I dot is being given by this, so ultimately replacing this term, we see this becomes omega bar cis cross rho bar I relative to j. So we can write it in this manner. So this is the equation that we are getting, particularly in case of plane motion. Particularly we can say, particularly in case of plane motion, in case of plane motion, we can say that we see that this omega bar cis, we can write that this omega bar cis, this vector is going to be perpendicular to the position vector this, or it is also perpendicular, omega bar cis, it is also going to be perpendicular V bar, or we can say that it is going to be perpendicular rho bar I relative to j dot. That means what I mean to say is that the angular velocity vector is going to be perpendicular to this green vector, as well as the angular velocity vector is going to be perpendicular to this relative velocity vector. Why I say is this, because if we see this last term is actually representing the vector triple product. So following the vector triple product relation, say if we have three vectors, A bar cross B bar cross C bar, we can write that this is equal to A bar dot C bar B bar minus A bar dot B bar of C bar. We know this equation from algebra, vector algebra. This is the outer vector. We remember it in this way. This is the outer vector. This is the adjacent vector. This is the remote vector. So it means ORA minus OR. This is how we can remember this vector triple product. So going by that relation, we can say from here, going by that relation, we can say that omega bar cis cross omega bar cis cross rho bar I relative to J, rho bar I relative to J will be equal to, so this is A bar, this is A bar, this is B bar, and this is C bar. So it is A bar dot C bar, means it will be omega bar cis dot rho bar I relative to J times omega bar cis minus, it is A bar dot B bar, so it will be omega bar cis dot omega bar cis of rho bar I relative to J. So since we note that we earlier said that omega bar cis is perpendicular to rho bar I relative to J, so ultimately you see this product becomes equal to 0. So it becomes 0 minus this omega bar cis dot omega bar cis is actually equal to omega cis square rho bar I relative to J. So for plane motion, we can see, if we do not take into account the space motion of the particles, if we see the plane motion, which we know that our objective is to first consider the plane motion, we note that this big term is ultimately equal to minus omega c square rho bar I relative to J. So what does that mean? It means therefore from here we can say, for in case of plane motion, we need to remember we are continuing this with our plane motion system. So we can see from this earlier equation that we can write from here, therefore we can say that rho bar double derivative of I relative to J is basically equal to omega bar cis dot cross rho bar I relative to J. Of course, it is going to be for plane motion minus omega cis square rho bar I relative to J. It is nothing but this is called the tangential acceleration, this is called the normal acceleration or centripetal acceleration, and we need to remember this is only true for plane motion. That is very important to understand. This is going to be true for plane motion. Now, why we say that? Because we have established the velocity equation over here. This is the velocity equation that we have, v bar I equal to v bar j plus omega c cross rho bar I relative to j. We can now come and differentiate this equation with respect to time. So what we get from here is something like this. We can therefore say that acceleration equation. So we can write now the acceleration equation. So we see that our basic equation for the velocity term is going to be equal to this: v bar I is equal to v bar j plus it is omega bar cis cross rho bar I relative to j. So if we differentiate it with respect to time, I will be getting a bar I. This we will be getting a bar j, a bar j, plus we have this equation. That means we can say this is actually, we can write it like this. This is actually v bar j plus this, we can say rho bar I relative to j dot. Correct? So rho bar I relative to j dot is basically this equation. We have already seen this. This is the equation we have already noted. So just saying that, we can say this is going to be rho bar I relative to j double dot. Now for plane motion, now we can see for plane motion, because mostly we have to discuss the plane motion here, the above becomes what? We get our equation something like this. We say that it is a bar I is equal to a bar j plus, we can see that it will be omega dot cis cross rho bar I relative to j minus this will be omega cis square rho bar I relative to j. So this will be therefore for plane motion, if we have a system of a rigid system, correct, rigid system comprising of two particles, consisting of a rigid system comprising of two particles, we see for them the acceleration equation can be written in this manner. So this is sometimes called three-term acceleration equation. About them we will be discussing in detail more when we will be technically considering the rigid body dynamics. But these equations will become helpful for us in case of our system consists of a rigid system like this. So when we will go and discuss the problems, we may identify such rigid systems in our domain, and then we can remember these basic equations and can apply our relevant equations of kinematics to simplify our problem. So students, with this we come to an end to the discussion of the dynamics of system of mass particles, and when we will be meeting once again, we will be taking up few problems highlighting the applications or explaining the applications of the theory that so far we have discussed. So at this point I stop my recording and thank you for watching the video.